All right, so we finished off yesterday and we were looking at the different types of problems you might encounter to do with specific heat capacity. So, quick review. Okay, specific heat capacity is how much energy is required to heat 1 gram of a material by 1 degree Celsius. Okay, that's what specific heat capacity is. All right, so you have a few problems here that are actually also in your digital workbook. So if it's too small to see there, you can see it on your phone. Okay, but we're going to do a little bit of problem solving, not too much because this isn't very difficult stuff. Okay, so we'll spend a little bit of time practicing that, go over anything that's unclear, anything that gives you trouble, and then I'm going to move on to latent heat, which uses this as well. Okay, but is going to talk more about how latent heat is able to carry energy from one place to another on Earth, why it carries so much energy, okay, all of that kind of stuff. So that'll be covered today as well. And then there'll be some problem solving to do with that. That's also not overly difficult. It's more time consuming. There's lots of steps, but all the individual steps are very easy. Okay, so we'll be doing that a little bit later on. So what I want you working on right now, okay, is just these problems here. Like I say, they're also in the digital workbook, which I may just pop up as well. Okay, the answers are in here in bold, right? So you can check them as you go. You will need the specific heat capacity chart that is in the digital workbook in order to answer these questions, right? Because you'll need to look up the C for many of them. Alrighty, questions on that? Okay. So in all likelihood, all you're going to see for a problem like this on a unit exam or a final exam is a simple problem, just like you've got here. Okay, I'm not going to ask you to do anything different. Okay, you're also going to use E equals mc delta T as part of doing a latent heat problem, but you won't have to manipulate the formula. You'll just be trying to calculate energy using the formula as given. Okay, so really this stuff is pretty simplistic, right? Which is why we always leave it for last. We like to leave the easiest stuff for the end when you've got lots of other stuff that you got to put together for your finals and stuff. Okay, so if there's any questions on that, we can go over them now. If not, I'm going to move on to latent heat. Everybody good there? Okay. All right, so latent heat works like this. There's both kinetic thermal energy and potential thermal energy in the same way that there's kinetic mechanical energy and potential mechanical energy. Okay, the differences are that in mechanical energy, I can change the potential energy and the kinetic energy of a substance or of an object at exactly the same time by just doing work. For thermal energy, that's not the case. For thermal energy, I can only increase kinetic or potential, but not both. Okay, so the only way to increase the thermal energy of something is to expose it to heat. Okay, everyone all right with that? Right, make it get hotter. Right, but as we know, all things change state at some point. Okay, so we're going to use water here because water is the most common example for us. Okay, if I start out and I have a bunch of ice at minus 25 degrees, okay, and I start adding thermal energy to it, what's it going to do? It's not going to melt right away. First, the ice is going to warm up. No, it's not going to melt. It's got to warm up first because ice only melts when it gets to 0 degrees Celsius. Okay, so I had ice at minus 25. If I expose it to heat, it doesn't melt right away. Okay, its temperature has to increase to its melting point. Now, when its temperature is increasing, what's happening to the particles of water, the little molecules? What's happening to them? They don't get further apart. They don't space out. They get moving faster, right? Okay, that's kinetic thermal energy. If I increase the temperature of something, I'm increasing its thermal kinetic energy. That's what a thermometer measures. Essentially, it measures the kinetic energy of the particles in a material. Okay, and it does that simply by having the particles run into the bottom of the thermometer. The more often there's collisions between the particles in the thermometer, the more energy is transferred to the liquid inside, the more it expands, and we see a warmer temperature. Okay, everyone all right with that? All right, so I keep adding heat. The ice gets to 0 degrees Celsius, and then it will melt. But what will happen to its temperature while it's melting? It stays the same. Okay, it just plateaus. The temperature will not change while the ice is melting because I can't change both the kinetic and potential thermal energy of water at the same time. Okay, so while I'm adding this heat and the ice is melting, the temperature will stay at 0 degrees Celsius. This is why ice keeps drinks cold. Okay, if I put ice in a drink, as long as the ice is in there, the drink stays pretty cold, right? Around like 3-4 degrees Celsius, somewhere in there. Okay, but it stays cold until the ice is gone. Once the ice is gone, then it actually warms up pretty quickly. But it'll stay cold as long as the ice is there. Okay, everyone all right with that idea? Okay, same thing for a cooler. You know, if you're packing for a trip on the weekend or whatever, and you're filling up a cooler with food and whatever, and you put ice in there, that food will stay cold as long as the ice is there. Once that ice is all melted and it's just water, it'll heat up real fast, and your sandwiches will get soggy. Okay, we don't want that. All right, so what we see here with this diagram is essentially what we call the heating curve of water, and it shows us what happens as we add energy to water. All right, so we've already covered this part of the diagram here, where we said I had ice at minus 25 and I added energy to it. It heated up to 0 degrees. All right, so I get it from minus 25 to 0. I keep adding heat. I keep adding heat at a constant rate. This graph here is showing us heat on the x-axis and temperature on the y-axis. All right, so we're talking about how much energy I'm adding, okay, and how much the temperature is changing. So for this part here, I add heat, and eventually all of the ice will be melted. If I continue to add heat at that constant rate, the water will begin to warm up. Now, water has a very high heat capacity. Okay? We talked about that yesterday and a little bit today. Right? That means I have to add a lot of energy in order to change its temperature. Right? We're talking here, like this is starting at about like 7 kilojoules, and I don't get it to boiling until I get to about 15 kilojoules. Okay, so that's 15,000 joules worth of energy, right, in order to get it there. So I add all of this heat, and eventually the water will start to what? It'll start to boil, exactly. Okay, when it's boiling, does its temperature change? No, it stays at 100 degrees Celsius until all of the water has boiled off into vapor or steam. Okay, now I want you to look at how much energy is involved in each section here. How much energy was required to heat the ice? Yeah, maybe something like that, maybe even less than that, maybe even just 1,000, right? This would be 5,000, this line here. Okay, so it didn't take very much heat energy to get the ice to 0. It took quite a bit more to melt the ice. Okay, it took a fair amount of energy to heat the water from 0 to 100, but look how much energy it's going to take to boil off all that water. Okay, it's like the vast majority of this entire graph is getting the water to become a vapor. Right? This is why I was saying this is going to explain to you how much latent heat is so important for transferring energy on a global scale. Okay? Look at how much energy is contained in water vapor. How much energy is required to make it vapor. When it goes somewhere else and it condenses, all of this energy is given off again. Okay? That's why you're always told as a kid, always be careful with steam, because steam can burn you way worse than water can. Okay? And it's not because steam could be greater than 100 degrees and water can't. It's because steam, if it hits your body, is not only already very hot kinetically, but it has a whole bunch of potential energy that it will release when it condenses on your skin. Okay, so you can get burned. Like if you had steam at 100 degrees hit your skin, it would give you like deep tissue burns, versus having water splashed on you at 100 degrees. Wouldn't hurt, it would burn you, but it wouldn't be nearly as bad because there's not as much energy in liquid water at 100 versus steam at 100. Steam at 100 degrees has this much energy. Water at 100 degrees has this much energy. Okay, so it's a huge deal, and that's why latent heat, the transfer of water vapor from one place to another on Earth, is such an important energy transfer mechanism. It holds lots and lots of energy. Okay, everybody all right with that? Okay, now I've heated up the steam. I've boiled it all off. Sorry, I haven't heated up the steam yet. I've got all steam. If I keep adding heat, will the steam get hotter? Yep, it'll get hotter. Okay, it doesn't take much to heat steam up. Once I get the steam heats up temperature-wise pretty quickly. All right. So everyone kind of following what's going on here. All right. If I wanted to calculate how much energy was required for this step where I was heating up the ice, okay, what formula would I use? No, I actually wouldn't use y equals mx plus b. Good guess, though. Okay? It's not a perfectly linear graph, so it's not what I would use. It's the one you were using this morning. E equals mc delta T, right? Because if I want to find out how much energy is required, I know the material is ice. I know it's going from minus 25 to 0, so I know the temperature change. As long as I knew the mass, I could use E equals mc delta T to figure out how much energy is required to warm the ice from minus 25 to 0. Okay, everybody all right with that? Okay, now here's where the one of the new formulas is going to come in. I can't use E equals mc delta T to figure out how much energy is required to melt ice, because what's not changing? The temperature. If I use that formula, it's going to tell me no energy is required, which is clearly wrong. Okay, I have to put energy in to melt ice. All right, so there's a different formula for calculating potential thermal energy, and there's a formula for calculating kinetic thermal energy. Okay? The formula for calculating kinetic thermal energy is E equals mc delta T. All right? For the latent heats, we use a slightly different formula that doesn't involve change in temperature. Okay, so in your notes, you should have this somewhere. Right, so latent heat is what we call it. We call it latent because it's not something that's necessarily measurable. Okay, it's something that happens when something changes state. So latent heat is the amount of heat that's involved in a state change, and this is true for any material, but we apply it to water more than anything because water is the most important thing. Okay, so it's hidden heat since the energy involved does not result in a change in temperature, and there are two kinds of latent heat. Okay, there's latent heat of fusion, which has to do with melting and freezing. And there's specific latent heat of vaporization, which has to do with vaporization and condensation. Right? So this has to do with the two, or each one of these has to do with a specific type of state change. Everybody okay with that? All right. So we'll first talk about latent heat of fusion. All right. This is what happens with melting or freezing. Okay. So it's the amount of heat required to melt 1 gram of a substance completely. Okay, with no change in temperature. Okay, so there's no temperature change during the melting process as potential energy is increasing, not the kinetic energy, right? So for water, the latent heat of fusion is 333 joules per gram. Okay. If I have 1 gram of snow in my hand, and 1 gram of snow is not very much, it's going to take 333 joules of energy from my hand in order for it to melt. Okay, is that a lot? Well, if you make a snowball with your bare hands, do your bare hands get cold pretty fast? Yep, it's taking a lot of energy away. Okay? It takes a lot of energy to melt ice. So if you're making snowballs with your bare hands, your hands get really cold really fast. Okay, for a couple of reasons. First off, yes, melting the ice does require a lot of energy, okay, from your body. But also, once that liquid water gets on your hands, what does it do? Well, it might warm up a little bit, but it also evaporates. Okay, and what is that going to make? How is that going to make you feel when the water evaporates? Okay, I want you to think about when you sweat. Why do you sweat? To cool your body off. Anytime water evaporates from your body, whether it's sweat or melted snow or whatever, it takes energy from your body to do it. That's why we sweat. Okay, it takes a lot of energy to evaporate water. So sweating is a really effective way of cooling us off because it can steal a lot of energy from our bodies in order to evaporate the water. Okay, same feeling. You get out of the shower. Okay, get out of the shower, you're immediately cold. If you don't dry off, you'll get chills. Okay, because the water that's on your body is starting to evaporate, and it's getting the energy to do it from you, stealing your energy in order to make it happen. Okay. All right, so what this means is that at 0 degrees Celsius, it takes 333 joules of energy to melt 1 gram of ice. It also means that if I have 1 gram of liquid water, it will give off 333 joules of energy when it freezes. All right, you probably noticed in the fall, okay, when ponds and lakes are starting to freeze, that steam kind of comes off of them. Okay, That's because energy is being lost rapidly by the water as it begins to freeze. Okay? It actually makes the air above the water a little bit warmer, okay, as the ice begins, or as the pond begins to freeze. Okay? All right, so the formula that helps us to calculate the amount of energy involved in melting or freezing is E equals M, so mass, times the latent heat of fusion, which is, for water and ice, this number, 333 joules per gram. Is that a pretty easy formula to use? Yeah, multiply two numbers together and you're good, okay? It's pretty straightforward. Okay, so if I put 3 grams worth of ice cubes in a drink, how much energy can they absorb? 990, well, actually just 999 joules, right? Because I'm saying I've got 3 grams of ice in the drink, it'll absorb 999 joules worth of energy while it melts. Okay, questions on that? All right. Vaporization works exactly the same, right? It's just we're talking about this part of the graph now, okay? And we know that that's a much bigger part of the graph, which is why the latent heat of vaporization is so big. It's 2,260 joules per gram. Okay? So for every gram of sweat that evaporates off of your body, okay, it could cause your body to lose 2,260 joules of thermal energy. Okay? That's why in the wintertime, if you're going outside for a while, you want to dress in layers. Okay? You always want to dress in layers, especially if you're going to be fairly active. Because if you're fairly active and you don't have layers, you'll eventually start to what? Sweat. All right, and you start to get hot and you're starting to sweat, so you go, okay, well, I'm just going to take my coat off. Will you get cold pretty quick? Yeah, but the worst part of it is whatever clothes you have on are wet. And the only way for them to dry is for that water to evaporate, and it's going to take the energy from you to do it. So if you're out there and you don't have layers on, you're working hard, you're sweating, and then suddenly you stop, you're going to get cold really fast, okay? And if you're out in the wilderness, that could be deadly. You could develop hypothermia because you don't have any dry clothes to put on, okay? If you dress in layers, as you start to get warm, you just take the layers off, okay? And then when you stop being active, you can put the layers back on again. Okay? It's also why we make certain types of clothing, okay, with the fibers that wick the moisture away. Okay? That way the moisture is out against like the shirt as opposed to against your skin like it would be in cotton. Okay? And that moisture evaporates without taking as much of your heat away. Okay? So all of those things are there to kind of thwart what happens with this. Okay? All right, so it's a lot of energy in order to evaporate water. So you imagine if you've got a moist air mass moving from the equator, okay, towards a more polar area, that could have millions of liters of evaporated water vapor in it. Okay, millions and millions of liters of that. And if that's the case, okay, is that holding a lot of energy? Yeah, okay, because a liter contains 1,000 grams of water. Right? And for every one gram of water vapor that's in that cloud, there's 2,260 joules worth of thermal energy waiting to be released. Right? So it's a lot of energy. Okay? The water cycle is a really important part of how thermal energy gets transferred, okay, around the globe. Okay, questions on that? All right, so we're going to move into kind of how this is going to work. Okay, so I want you to write this question down, and then I'm going to walk you through how you solve one of these problems. The math is really, really easy. Okay, there's nothing difficult mathematically about this. It's just there's a lot of steps, so it's time consuming. So here's how a question like this starts. I can identify it right away as a latent heat problem because it can't be solved in one step. Okay, I can't just go, oh, how much energy is required to heat 250 grams of ice at -15 into steam at 150 degrees? Okay, that's more than like 1 E equals MC delta T problem. Agreed? Okay, because we're talking about ice, then we're talking about water, and then we're talking about steam, which all have different specific heat capacities. Okay, and that's one of the most common mistakes I see when people are solving these kinds of problems, is they just do this as one step, okay, and use the same specific heat capacity the whole way along. Water is weird, okay? It's that polar molecule thing. It has a different heat capacity depending on what state it's in. And it's one of the very few materials that's true for. All right. So the first thing I want to do when I see something like this, and I know there's going to be at least one state change, is I want to draw the heating curve of water that we looked at just a minute ago. It doesn't have to be like super accurate. I just need to draw the shape. Okay. So this is the heating curve of water. This is the part. Okay. Part one here is where ice is being warmed. Okay, where I'm heating up the ice. Part two is where the ice is melting. Part three is where I'm heating up the water. Part four is where I'm vaporizing the water. And part five is where the steam is being warmed. Okay? Everyone all right with that? Okay, so once I've got the heating curve drawn, then I want to mark the start and end points of this problem on it, so I know how many steps I'm going to have to do and what steps I'm going to have to do. All right, so it says we're starting with ice at minus 15 degrees. So that means I'm starting down here somewhere. And I'm going to end up with steam at 150 degrees. So that means I'm ending up here somewhere. So how many steps am I going to have to do? 5. Okay, I'm first going to have to warm the ice to 0. Then I'm going to melt the ice. Then I'm going to warm the water. Then I'm going to evaporate the water, and then I'm going to warm the steam. Okay, that's going to be 5 separate steps. On a unit exam, I probably wouldn't give you one with 5 steps because it just takes too long, and I know you can show me you can do it with like a 3 or a 4 step one. Okay, so now that I've identified that, and incidentally, on a test, that would be worth a mark. Okay, identifying how many steps you have to do. Okay, so then I need to write the steps down. Okay, so there's my steps. So in step 1, I'm heating ice from minus 15 to 0 degrees Celsius, right? What formula am I going to use for that? I want to calculate the amount of energy I need to heat ice from minus 15 to 0. E equals mc delta T, okay? How do I know that's the formula I need to use? Yeah, I have all the stuff for it, and I'm changing the temperature. Okay, in step 1, this is a change in kinetic thermal energy, so I have to use the kinetic thermal energy formula. Right? So for step 1, that's going to look like this. I have 250 grams of ice times the specific heat capacity of ice, which is 2.116 joules per gram degree Celsius. Okay, and then multiply that by the temperature change, 15 degrees. All right, everybody okay with that? All right, so we'll calculate what that number is going to be. Okay, so we got 250 times 2.116 times 15 degrees. All right, so we're looking at 7,935 joules. Okay, so on a test, you would get a mark for this and a mark for that. Okay. All right, for step 2, in step 2, I have the ice at 0, and at the end of step 2, I'm going to have water at 0. So I'm melting the ice during step 2. What formula helps me calculate the amount of energy required to melt a certain amount of ice? Right, E equals M times the latent heat of fusion, or E equals MLF. Okay, and by the way, on a test, you would be given that number, the 333 and the 2,260. You don't have to memorize those numbers, okay? They'll be given to you on a test. All right, so that's the formula I'm going to use because it involves the melting of ice. So what's my mass? Is it still 250? Yes, okay? It doesn't matter what state the water's in. The 250 grams is due to the number of water molecules that are present, and that number isn't changing, okay? So 250 times 333. Okay, so 83,250 joules. So a significantly larger amount of energy than it took to warm up the ice. So at the end of step 2, I'm right here. I have water at 0 degrees Celsius, and I'm headed for water at 100 degrees Celsius. What formula am I using here? E equals mc delta T, because I'm changing the kinetic thermal energy now. I'm changing temperature. Okay, so that'll be 250 grams times, what specific heat capacity do we use here? Water, right? Liquid water. So that'll be 4.2 joules per gram degree Celsius. Okay, times, what am I changing the temperature by? 100. Okay, and guys, this is another very common mistake that people make. Okay, I will often see people forget that I only have ice from minus 15 to 0. So the temperature change here is only 15. I only have water between 0 and 100. But what I'll often see is people will do the total temperature change, and they'll plug that in every single time there's a delta T. Right? I'm not changing the temperature of water by 165 degrees. Right? Over the whole question, yes, okay, it does change by 165 degrees, but it's by section. Okay? In this section here, I'm only changing the temperature by 100. Okay? Everyone okay with that? That's also a very common mistake. Okay, so we've got 250 grams times 4.2 joules per gram degree Celsius times 100 degrees. All right, so we're looking at 105,000 joules. Sorry, 105,000, right? Yeah, joules. All right, so a bit more than it took to melt the ice for certain, okay, but around, still a similar number. When I get to step 4, I have water at 100 degrees, so it's boiling. Okay? At the end of step 4, I'm going to have steam at 100 degrees Celsius. Right? The temperature is not changing here, so what formula am I going to use? Now I'm going to use E equals M times LV, okay, the latent heat of vaporization. Okay, so that's going to be 250 grams, because the mass doesn't change, times 2,260 joules per gram. All right, 565,000 joules. Okay, and guys, this is like 1 cup of water. Okay, it's 250 milliliters. It's not a lot of water. Okay, but it's already far more than the total of the rest of this question. Okay, just to evaporate the water took more energy than all the other previous 3 steps. All right, at the beginning of step 5, I now have steam at 100 degrees Celsius, and I'm headed for 150. All right, so now I'm back to a change in kinetic thermal energy. So I'm back to E equals mc delta T. All right, that's going to mean 250 grams times 2.02, okay, because the specific heat of steam is different, 2.02 joules per gram times 50 degrees Celsius. I'm only heating the steam from 100 to 150. Okay. All right, so we're looking at 25,250 joules. Okay, so has there been like any really difficult math here? We're just plugging numbers into a formula, right? All we got to make sure is that we pick the right numbers. Okay. All right, what do I have to do with all these numbers now to get my final answer? Add them all together. Yep. Okay, so plus 565,000 plus 105,000 plus 83,250 plus 7,935. Okay, so this is going to require 786,435 joules. Okay, so essentially we took about, a cup of snow, melted it, okay, heated it to boiling, boiled it off, heated the steam by another 50 degrees, right? And that took 786,435 joules worth of energy. All right, questions on how that works? Well, if I gave you a 5-step one, probably be between 10 and 12. All right, just by step, which is why on an exam, I wouldn't give you a 5-step one, because then too much of the exam was based on just this one topic. Like if your exam's out of 60, it's, the fifth of the test. It's not right. Okay. What's that? Well, it's easy marks, but it kind of skews everything else in the unit to being unimportant when 1/5 of the material is, or 1/5 of the marks is this one question, right? So it wouldn't work that way. Okay, you would have a latent heat problem. There will be one on your unit exam. It'll work like this, but it won't be 5 steps. No, I don't remember what it's at. I was just saying if it was out of 60, this would be like 20% of it, right? Okay, by the way, speaking of your unit exam, I did pick the date for that. It's going to be January 17th. We'll be done the unit. We'll be doing like final exam review and stuff. But I needed to make sure that we were doing that on a day when there weren't diploma exams and stuff like Part A's or anything going on. So that's the day it's going to be. Okay? I would have liked to have had it on like the Tuesday, but there's diploma exams and stuff going on that week. So, all right, so that's when it will be. Okay, make sure that you are ready for it. All right. Any other questions on how this one worked? Okay. All right, so what I'd like you guys to do is, this is going to be, you're going to have to synthesize some answers here. I want you to think about what the answer to some of these might be when you write them down. Okay, so you may need to write, a couple of sentences to explain what you think about these questions here. And when we get to question number 5, that's going to be like the problem that we just did. All right, but for right now, I want you guys to do questions 1 through 4. Okay, write down some explanation answers, and then I want to go through them and just make sure we're understanding how this concept works. All right, so question number 1, we kind of talked about already. Why does putting ice cubes in water, or in a drink, keep your drink cold? Okay, well, if I put them in there, they're below 0. So first off, they're going to warm up to 0 degrees. And where are they taking that energy from? From the drink. Okay, and then conversely, we also have that now they're going to melt, and they're getting the energy for that from the drink. So the drink keeps giving energy until the drink is down to the same temperature as the ice cubes, okay, according to the law of conservation of energy. And then most of the energy required, or that melts the ice after that, is actually coming from the surroundings. Okay? Once you get the drink and the ice cubes to the same temperature, then the second law of thermodynamics says there's no more heat transfer between these two items because they're the same temperature, right? But obviously the surroundings would be warmer, okay? And as a result, the energy to melt the ice will come from the surroundings, but it'll still keep your drink cold until all of the ice is gone, all right? Everybody all right with that idea? Okay. We sweat. It's stinky, it's smelly. Some people sweat more than others, okay? But it cools us off. Now, it cools us off because in order to evaporate, it has to take energy from our body to do it, okay? It's as simple as that. Now, if you perspire, so you like sweat very little, okay? Or you're like, drenched in sweat very quickly, does that mean, like if you're drenched in sweat, does that mean that you cool your body better than someone who only perspires? It doesn't. In fact, having just a light sheen of sweat on your skin is actually best for cooling you off. If you're drenched, the surface area isn't as good, okay, and you don't actually cool yourself any better, okay, than you would if you just had a small amount of water on your body. That's why, like on a really hot day, if you just get a little bit of mist kind of on your face or on your skin, it feels really refreshing because it very quickly evaporates. Okay, whereas like if you dump a bucket of water on your head, it's awesome. There's water there for a lot longer. Okay, but it's different, right? But yeah, being like a heavy sweater doesn't necessarily mean that you're cooling your body any better. Okay, like back about 10 years ago now, the Oilers had Nikolai Habibulin as their goalie. Okay, this guy sweat like crazy. He would lose 10 pounds in a game, okay, in just water. He would come in every time there was a stoppage in play. He'd come over to the bench and get a new blocker and a new catcher because they'd be soaked. Okay? They actually caught on the crease cam one time. He had holes drilled in the bottom of his skates to drain the sweat, and they actually caught it on the crease cam. Sweat dripping out the bottom of his skates. Okay, like this guy he sweat like crazy, which is why, of course, the Oilers were so bad in a shootout, because by the time shootout came, the guy lost 10 pounds. He was dehydrated. Okay, like he was just going through water like crazy. But okay, yeah, so it's certainly a lot. Some people sweat a lot more, but it doesn't necessarily mean they cool their body any better than someone who perspires. Okay? All right, question number 3. Gardeners will often spray their crops before a frost. And what I mean by spray is they'll put like a light coating of water on the crops. Okay, why is that going to keep the fruit and the leaves from freezing? What's the water going to do when it drops below freezing? It's going to freeze. Now, when water freezes into ice, energy is lost. It's released. Where does that energy go? Into the plant. Exactly. Keeps the plant from freezing. Only works if it's going to be a light frost. If it's going to get down to -10, you're screwed anyway. Okay, everything's going to die. But if it's just going to be a light freeze, it can keep like things like tomatoes and like apples and stuff like that from getting having their quality significantly reduced. Okay, it doesn't necessarily destroy them, but it would reduce their quality considerably. Okay, which is better at keeping food in a cooler cold, 10 kilograms of ice at 0 or 10 kilograms of water at 0? Ice, yeah, because it's got less thermal energy than the water does. It has the ability to absorb more heat from whatever's in the cooler than the water does. The water is already a liquid. Okay? It doesn't have that ability to change state like water does, and that takes a lot of energy to change the state of ice. So okay, it's going to have the ability to at least absorb more energy that way. All right, for question number 5 is asking us how much heat is given off when 2 kilograms of water at 0 degrees freezes into ice at 0 degrees. All right, how many steps does this question have? 1. Okay, there's no temperature change here, right? It's starting at water at 0, freezing into ice at 0. The only step here, if we're drawing the heating curve of water, is this step right here, okay, where we freeze water. So all we have to do is go E equals MLF. Okay, we take our 2,000 grams. Remember, it's got to be in grams. That's a trick, right? Put it in kilograms. Okay, times 333 joules per gram gives us 666,000 joules. Okay, everybody all right with that? So it's important to be able to read the question carefully, use the heating curve of water diagram to decide how many steps do I have here. Okay, is number 6 similar to number 5? Okay, I start with water at 100 degrees. I'm moving into steam at 100 degrees. Again, there's no temperature changes here. Okay, there's just a state change from 100 to 100. Okay, liquid water to steam. So the only calculations I have to do here is M times LV. So that's 2,000 times 2,260. Okay, sorry, not 2,000. It's not 2,000 grams. It's 0.06. So that's 60 grams. Okay, times 2,260 gives me 135,600 joules. All right. So fairly easy calculations. All right, we will work on a couple more of those tomorrow. Okay, we'll kind of leave it at that for today, but we'll work on a couple of multi-step problems tomorrow, and then we'll be moving on to the next thing here. All right. So guys, remember your climatogram activity is coming up due here on Friday. So make sure that you're getting that done. Okay, if you were not here before Christmas when we were working on that, you've got a bit of work to do. Okay, there's a podcast and all that kind of stuff on Google Classroom to tell you what to do.